Hello, my name is Brian Hernandez. Today we're going to be talking about surge protectors in an LRC circuit for our physics project. What is an LRC circuit? An LRC circuit is an inductor resistor capacitor circuit. An inductor builds current using a magnetic field. If you were to start to charge an inductor with zero current, there would be zero magnetic field. But as the current rises, so does the magnetic field, which leads to the energy stored in it. Like I said, will be growing. Resistors we've worked with, they oppose current, so the energy dissipates. Capacitors store energy between two plates, and after they are charged, they can release that current. With inductors, the strength of the magnetic field is proportional to the amount of current through its coil. With the energy storage in an inductor, the amount of magnetic energy stored is based on the number of turns the coil has and the material that the core is made out of. A change in magnetic field leads to an induced voltage, which opposes the current. This is called Lenz's law. What is a surge protector? A surge protector is a device that is designed to protect electronics from spikes in voltage. These can be caused by lightning strikes or power outages, or just from simply turning on a power supply. Surge protector works by using the properties of inductors, resistors, and capacitors to limit the amount of current / voltage going into an electronic by either blocking the excess voltage or shorting it directly into a ground. In a LRC circuit, a surge protector would use an inductor to smooth out any spikes in current. A resistor would be used to dissipate the energy, getting rid of the unwanted voltage. Capacitor would be used to store that excess energy and safely dissipate it into a ground. The most common kind of surge protector is an MOV. There's a lot of different kinds. When a voltage spike occurs, the MOV will change from high impedance to low resistance. By connecting to a ground wire, the MOV will dissipate the excess current caused by the voltage spike and safely put it into a ground wire. Here's a diagram of how it works. A fuse is normally in these circuits. It's kind of seen as a failsafe. If it's just too much, the fuse will blow and no current will flow through the circuit at all. If our MOV can handle 250 volts and our supply voltage is less than 250 volts, the voltage will come through the MOV. We'll see it's less than 250 and it will have high resistance. So we'll continue to move and go through the whole circuit. If our supply voltage is greater than 250, the MOV will see this and turn into low resistance mode, and it will pull the current, take it, and dissipate it into a ground wire. Some equations, some information. Induced voltage, we just learned about this. Where the direction of the current matters, and it will tell you if the inductor is losing or gaining energy stored in an inductor, where U is the energy stored in the inductor, L is the inductance, and I is the current flowing through the inductor. Some assumptions. We are working with ideal wires, resistors, inductors, and capacitors. We're assuming that the circuit is only to be explained using LRCs. We're going to talk about MOVs and focus on MOVs, and touch on fuses, but not include them in our diagram too much. We're using the same formulas to add resistors and capacitors in series and in parallel. We've done this in class before. And then yet again, the voltage across an inductor and potential energy of an inductor. And then here is a diagram. So as you can see, with this circuit open, our capacitor charges charges the plates and then pushes it one way, charges and it pushes it the other way. But as soon as we close the circuit, you can see that the inductor here does not just oppose all of the current and get rid of it. It over time acts as an ideal wire. And just touching again on some similarities of how this all relates to stuff we've done previously. We've worked with capacitors, we've worked with resistors, and we just touched on inductors. You can use the same formulas to add them in series and in parallel. We can also use the same equation to charge or discharge a capacitor.
All right, hey guys, my name is Jesse Noden, and I'm just going to go over some sense making. So, to make sense of our circuit, we're going to do a special case. So, what if the circuit was without a metal oxide resistor, or MOV? What would happen to the circuit if a voltage spike happened? So, like Brian said, the MOV is a circuit surge protector. And let's just hypothetically, let's say there's a power outage that overwhelms a circuit. Without the MOV, to ground the sudden surge to activate as the ground, the electronic that is receiving power will blow. So it'll like, and just some basic math using Ohm's law, you could figure out what happens. So we have V equals IR, and we have a voltage surge of 240 volts. This would double the current if the current could handle it. So solving for the current surge would be 200 volts divided by the R resistor. If R had a normal operating current of 10 amps at 120 volts, then we would set it equal. So 120 equals 10 R. And this gives the resistor 12 ohms. When we substitute in, we get the current surge, which equals 240 divided by 12, and that's 20 amps. So this is twice the safe operating current of the circuit. So you could imagine that that circuit was powering a light bulb. And with that voltage surge, and if the light bulb didn't have a surge protector, the light bulb would like pop, like you see in the movies where it goes. So that's what happens when we don't have a surge protector, an MOV. So a little bit about the reflection and similar problems that we've done in class. So we have done some problems related to capacitors, and this problem on the right is from week 7 lecture. And it had us looking at the capacitors in series. So these capacitor problems really helped us with the idea of the of capacitors and the whole LRC circuit. And we chose to have our capacitors in parallel because we wanted to increase the total capacitance. So, so a similar problem for the inductor. So in the last week of class, we worked with inductors. We learned that an inductor, if it has increasing current, will drop voltage. If the current is decreasing, the voltage drop is positive. So this is similar to our problem because a uh, metal oxide varistor has an inductor in it. In a sense, an inductor acts as a surge protector. It always wants to oppose current. So that really helped us with understanding inductors.
This is Abdullah, and here, moving on with the inductors examples, the second one. So here, an inductor is a device that can oppose the changes in the current fluctuation. And if the current is increasing, it will resist that change and try to minimize that change. Similarly, if the current decreasing, it will increase it This principle is inspired by Lenz's law and is very useful in protection against sudden spikes in the voltage. So, as shown in the inductor examples in the circuit diagram that it shows on the right side, so we're having a battery with 6 volts and an inductor, a switch, and a neon light, a neon bulb. So when the switch was closed, it wasn't even enough to light up the neon bulb because it usually needs a 70 voltage to light up. So we can see clearly that it hasn't lit up. Moving on to the one to the right, here we have our switch is opened. So there was a high resistance introduced that causes current to decrease. So induced voltage uh, counteract this, producing around 70 volts and light up the bulb. So when the switch was opened, the inductor have worked and produces the 70 volts that's needed to light up this bulb. All right, here we have a similar example to what we've had in class. So here, a resistor example. In class, we had an example involving a power source and 3 resistors. 2 of them are in series. We can relate this to our problem because in MOV, to provide the most amount of resistance, the resistor need to be in series. Adding resistors in series is the same in both cases. So here, it was the exercise 2 in one of the classes that we've had, and it shows this. All right. And even on one of other classes, we've had a capacitor example where basically, so capacitors can store energy by choosing the correct capacitance value. Electrical energy can be stored in the capacitor itself and released at a slow rate. In this way, the peak voltage and peak current are reduced. This problem, this problem from the lecture 10. Capacitors helped us choosing the capacitance such as that it could release or store excess energy as required to suppress surges or stop surges. And this is the example on the right where it asks us what happened when work added to capacitor as it changes. So it is stored in the capacitor and it can become a kinetic energy of the changes of the charges. Sorry. So where do we mostly need surge protectors? I've added 5 main points where we really need them. Why do we need surge protection protectors? I've added 4 points, and they're mostly about protecting us, so it preventing damage and shield electronic devices from sudden voltage spikes, which can cause beyond repair damage. And it can increase the lifetime and reduce stress on components and manage power flow to extend the life of expensive electronic devices. And it can ensure the safety of our use for the electronic devices from any surge spikes that happen. And it could help us to maintain the performance for our devices at optimal levels, providing a stable and consistent power supply. These are some examples and why we need them, but there could be more things that we haven't mentioned. And last of all, this is our sources, and thank you.